So now we're going to talk about Friedel Crafts' acylation of a benzene ring. And so benzene, we know, is not all that reactive. We have to make a really good electrophile for it to act as a nucleophile. What we're going to do is we're going to take acyl chloride and get to the product, which is this ketone species. And so this reaction on its own won't work. We have to make the acyl chloride into a better nucleophile, or excuse me, better electrophile, and we do that by using aluminum trichloride. So the first step of this reaction is activation of the acyl chloride. So the chlorine coordinates to the aluminum of AlCl3. What we've done here is basically pulled electron density from the chloride onto the aluminum. This makes the carbon center of the carbonyl here more electrophilic, and electrophilic enough that the pi electrons of benzene will attack, and we'll kick out the acyl chloride. Excuse me, we'll kick out the chloride. And so, as we have the acyl group now attached to the double bond here, we leave behind a carbocation on the carbon next door. This carbocation has resonance stabilization, so we can move the pi electrons of the ring around. And so we can come to have a new carbocation. We can have one more carbocation in which we flip the electrons around further. And what we'll see is that this new carbocation that we've just made looks very similar to the initial carbocation, but the positive charge is shared over all three resonance structures. The carbon with the acyl group on it still has a proton present. And so we've kicked out a Cl- in this case. And so Cl- can come. The driving force is re-aromatization of the ring. We remove the proton, give the electrons in the carbon-hydrogen bond to satisfy the carbocation and to access the product. And that's how you do a Friedel Crafts acylation.